Oh, hello everyone. I am Suvrat. Am I audible? So we'll be discussing starters 211 code chef. So can someone confirm if I'm audible? Hello. Okay. So let's start the discussion. So the first problem is buying chairs. Chef is redecorating his house and is now trying to decide which chairs to buy. The furniture store chef is visiting has W wooden chairs and P plastic chairs available. Chef believes that each wooden chair will increase the stylishness of his house by 2, while each plastic chair will increase the stylishness of his house by 1. Chef wants to buy exactly K chairs in total, and it is guaranteed that K is less than equal to W plus P. Find the maximum stylishness chef can attain by purchasing exactly K chairs from the store. And the constraints are very small. So, problem A. Basically, we have W wooden chairs and P plastic chairs, and wooden chairs increase our style by +2, and plastic chair increase our style by +1, and we need to buy a total K chairs and find maximum stylishness. So basically, this is a very simple problem. We obviously need to buy as many wooden chairs as possible, and then we can buy the plastic chairs. So if the number of wooden chairs is greater than equal to K, then the answer would obviously be 2 into W, 2 into K, because all the K chairs we'll be buying would be wooden. Else, we need to buy the maximum number of wooden chairs we can, and then the rest will be plastic. So K minus W plastic chairs. So these would be wooden, and these would be plastic. And here all of them are wooden. So this would be the solution for this problem. And the solution is O of 1. So I'll show you guys the code. The test case also, we can see that the first test case W is less than equal to K. So 4 wooden chairs and then 2 plastic chairs we'll buy. So 4 into 2 plus 2, 10. Then we will buy, since 4 is greater than 2, we'll just buy 2 wooden chairs. So the answer will be 4. Then again 6 wooden and 3 plastic. So 12 plus 3, 15. Here 3 wooden, so 6. So the code will be just as I told. If W is greater than equal to K, then simply 2 into K, else 2 into W plus K minus W. So that was the solution for problem A. If you guys have any doubts, you can ask. So I think you guys don't have any doubts. So let's move on to the next problem. So the next problem is wolf down. A certain forest has n animals living in it. Each animal is either a wolf or a bird. Curiously, all the animals live on a straight line at positions 1, 2, 3 till n on the x-axis. You are given a binary string S of length n where Si is equal to 0 means that the animal living at the position I is a bird, and Si equals to 1 means the animal living at the position I is a wolf. Unfortunately, the wolves like to eat the birds. For every second, the following will happen. For every position x, such that there is a wolf at a position x and a bird at position x plus 1, the wolf at position x will eat the bird. And after eating the bird, the wolf will move to position x plus 1. Note that birds never move. A wolf that doesn't eat a bird doesn't move, and each wolf eats at most one bird in every second. A bird is called safe if it never gets eaten by a wolf. How many birds in the forest are safe? And the constraints for the problem are again very small, so likely n cube will also pass. Problem B. So we are given a binary string S where 0 means that the 0 means Si is a bird and 1 means Si is a wolf. And every second the following happens. If at some position X there is a wolf and at position x plus 1 there is a bird, then wolf will eat the bird and move to position x plus 1. So we need to find how many birds will never get eaten. Let's see the test cases. So the first test case is 0, 0, 0. Since we know that 0 is a bird and 1 is a wolf, so these are all birds. So obviously, since there is no wolf, no bird will get eaten. So the answer for this test case will be 3, since all of the birds are safe. The next test case is 1, 1. Again, now we don't have any birds. So again, there will be 0 birds. Safe. The next test case is 1, 0, 1, 0, 0. So what will happen now? So basically, this will be wolf, bird, and bird. So after the first second, this wolf will eat this bird and this wolf will eat this bird. So basically wolf, then this position will be now empty, then a wolf and bird. Then again in the next second, this wolf will eat this bird. So wolf, empty, empty, wolf. So after 2 seconds, all birds will be killed. So answer for this test case is 0. 0. Then the next test case is 0, 1, 0, 0. 0, 1, 0, 0. So this will be wolf, bird, bird, wolf, bird, bird. And after the first second, this wolf will eat this bird. So bird, empty, wolf, then bird. And in the next second, this wolf will eat this bird. So basically, the answer for this test case will be 1. So we see a pattern that all the birds in front of any wolf will get eaten by that wolf one by one. So basically, these 2 birds will get eaten by this wolf. This bird will get eaten by this wolf. So basically we can say that if our test case looks like this and so on, so these two birds will always get eaten by this wolf, these two birds will get eaten by this wolf, these will get eaten by this wolf, and even if we have two wolves, again these four birds will get eaten by this wolf. So no bird will be safe that comes after a wolf. No bird will be safe that comes after a wolf. And since wolf can only eat the bird at position x plus 1, it will never eat the bird at position x minus 1. So the wolf will eat every bird in front of it, like that. So using this observation, we can say that the safe birds will be those which do not have a wolf before them. So essentially, these would be the zeros that are in the starting of the binary string. Starting of the string S. So basically, if the string S looks like this 0 0 0, then 1 0 0 1 0 0. So these would be the birds that do not have a wolf before them. So these would be the safe birds. So in the first test case, since all the three were in the starting, so answer will be 3. Then in the next test case, there were no zeros in the starting, so 0. Then again no zeros in the starting, so again 0. Then we have 1 0 in the starting, so answer is 1. So we just need to count the number of zeros in the beginning and that will be answer. And how can we do that? We can simply iterate from 0 to n, and we can break if s of I is 1. We can just break, else we can just count plus plus, and this count will be your answer. So the solution for this problem would be O of n, which will get accepted since these are small numbers. So I'll show you guys the code now. So I take input string s, then for I equal to 0 till I less than n, and this is that break condition. We will only move forward in the loop if si is equal to 0, else the loop will get broken, and answer plus plus, and then see out answer. So this was the code for problem B. So if anyone has any doubts in this problem, they can ask. I'll come back from the washroom in a minute. Okay, so I don't think you guys have doubts. So let's move on to problem C. Okay, so problem C is no doubling. For an array A of length n, we define f of A as follows. Let S denote the sum so far and H denote your happiness. Initially, S and H are both 0. Then for each I from 1 to n in order, if S doesn't double upon adding AI to it, add 1 to your happiness. That is, if S plus AI is not equal to 2S, then add 1 to H. Note that if S plus AI equal to 2S holds, instead H does not change. Then add AI to S. So f of A is defined to be the final value of H. To see an example of f of A being computed, see the samples below. You are given an array A of length n. You are allowed to freely rearrange this array however you like. Find any rearrangement of A that maximizes f of A. If there are multiple rearrangements that maximizes f of A, any of them will be accepted. And the constraints for this problem are n is less than equal to 2e5, test cases are 1e5, and AI is still 1e9, and we are given the sum of n across all test cases will not exceed 2e5. So the expected time complexity for this problem would be O of n and O of n log n. O of n square would be too many operations. So let me explain the problem. Problem C. Basically, we are given an array. Basically, let's first understand the definition of f of A. What is f of A? Let's say we have an array A1, A2, A3, A4, A5, and so on. What we will do is we will start from left to right, and let's say that the current score is S, then if S plus AI is equal to 2S is not equal to 2S, then our H increases by 1, else our H remains same. And after we do this, we will just increase S with AI. So let's take an example to understand how f of A is calculated. So let's take this only, consider the arrangement this, f of A is computed as follows. So let's take 2, 3, 1. So initially S is equal to 0. Now we see that S plus 2 is not equal to 2S. So initially S is equal to 0. So we see that S plus 2 is not equal to 2S. Clearly, since S is 0, 0 plus 2 is not equal to 0. So our happiness will be 0. Our happiness will increase by 1 and S will become 2. Then again we see that 2 plus 3 is not equal to 4. S and 2S. So again our happiness will increase by 1. So this will become 2 and S is now 5. Then again we see that 5 plus 1 is not equal to 10. So again H will increase by 1 and this will become 6. Now if the next element was 6, then basically 6 plus 6 is now equal to 12. So now our happiness will not increase, but our score will now become 12. So basically score is the prefix sum, and if the current element is equal to the sum of all the last elements, then our happiness will increase. So we can say that if AI is equal to sum of I equal to 0 till actually j equal to 0 till j minus 1 aj, then happiness will not increase at AI. So this is the this is what we understood from the definition of f of A. So if AI is the sum, basically 6 was sum of 2, 3, 1. So happiness did not increase at 6. But 1 was not the sum of 2 and 3. And 3 was also not the sum of 2. So happiness increased here and here, but it did not increase here. So this is the definition of f of A. and the problem is basically we are given an array A. We need to rearrange it so that it maximizes f of A. We need to rearrange A so that it maximizes f of A. That's what we need to do. So let's see the test cases now. So the first test case is we only have one single element, so there are no rearrangements possible. So that would be the answer. Then the next is 2, 1, 3. 2, 1, 3. So 2, 1, 3. So let's try to calculate the happiness value without rearranging. So initially S would be 0. What will happen? S will become, let's just do this, S. So S will become 2 here and happiness will become 1. And then again 1 is also not equal to the sum of previous elements. So happiness will become 2 and S will become 3. Now 3 is equal to 2 plus 1. So happiness will not increase and the score sum will become 6. So basically if we do not rearrange, the happiness will be 2 only. So we need to rearrange in a way that AI is not equal to sum of j equal to 0 till j minus 1 aj. So we need to make sure that this condition is followed as much as we possibly can. So what we can do is if the sum of elements before AI is greater than AI, then this condition will never be true, right? So for now, let's just what happens if we take this arrangement 2, 3, 1, 2, 3, 1. So H and S. So S will become 2 and H will become 1. Now again 3 is not equal to 2. So H will become 2, sum will become 5. Now 1 is not equal to 5. So H will become 3 and sum will become 6. So basically what difference was from this arrangement to this arrangement? Here 2 plus 1 was equal to 3. But here 2 plus 3 was not equal to 1. So why? Because there is this element which is greater than 1 before 1. So because of this, the sum can never be now equal to 1. So what we can do is we get this hint from this test case that we can place the maximum element in the first position. So if we place the maximum element in the first position, so then the sum of these values will be pretty much every time greater than this value, except in one case. We will discuss that as well, but most of the time it will be greater than this value since this is the maximum element, right? So this cannot be greater than maximum element plus some more elements. So let's for now just see the next test cases. So 4, 2, 6, 2, 4, 2, 6, 2, 4, 2, 6, 2. We see that our score will increase here, our score will increase here, but then our score will not increase here because 4 plus 2 is equal to 6. So here our score will not increase. Again, here our score will increase. So if we do not rearrange, our score will be 3 only. But if we place this 6 element in the beginning, what will happen? 6 in the beginning, then 4, 2, 2. So again plus 1, now 4 is not equal to 6 plus 1, 2 is not equal to 10 plus 1, 2 is again not equal to 12 plus 1, so 4. So obviously these elements will never be able to be equal to 6, right? Is that always true? So the next test case is 1, 1, 1, 1, 1, 1. So now there is no maximum element, right? So this we will have +1, and then we will have +0 here, and then we will have +1 here. So the overall will be 2 only, and we cannot increase the score anymore because there are no other rearrangement than other than this. So what happened? So basically, if we place the maximum element here, then in only one case, we will miss this point of happiness if this is also equal to maximum. And basically, the values after that, they will always give a happiness point because they would be maximum plus what a of 1, let's call this a of 1 and a of 0. So maximum plus a of 1 will be always greater than the maximum value present in the array. So these elements will always be smaller than the prefix sum. So we don't need to worry about these elements. We just need to ensure that if we can, we need to make the second element not equal to the maximum element. Because if it is equal to the maximum element, then we won't be able to increase the happiness here. So now our question is split into two different cases. One where all the elements are same, because basically we are given the array like this 3 3 3 3 3. Let's just take some a. So in this case, the maximum happiness will be n-1, since there are no other rearrangements possible, and we will have a +1 on every number except this number, because this is a is equal to a. So in this case, n-1, and in the next case, if we have just one number different, let's say we had the array as a and we had one b, and we are given that a is greater than b, then we can simply do this a. So what will happen? Now a is not equal to b, and a plus b will be now greater than all of these. So if there are different elements present, then happiness will be n only. And corresponding arrangement could be anything like maximum value. Then we can just place the values in any order. We just need to make sure that this is not equal to the maximum value. Because if this is equal to the maximum value, so then these two will be equal and our happiness will not increase here. But if this is some other value other than maximum, then our happiness will increase here. And once our happiness will increase here, all the other points, we will always increase our happiness. So we can follow one strategy to implement this. What we can do is we can place the maximum value in the front, and we can just put the sorted array here. Sorted array of remaining elements. So in this way, in this case, if there is some other number present other than max, then that number will come here, because it will obviously be less than max, since max is the maximum of their array. Else this whole array will be just max. So this would implement our solution pretty nicely, and sorting will take O of n log n, so the solution will be O of n log n. I'll show you guys the code. So basically, we take input the vector v, then we sort it, and then we create the answer vector where the first element will be the maximum element, and then we push back the rest of the elements in sorted arrangement, and then we see out the array. So this was the solution for problem C. If anyone has any doubts, they can ask. Reverse sort, basically reverse sort is a very good approach, but what will happen if we have the array 3 6 6 4 5 4? So basically in this case, when we reverse sort it, it will become 6 6 5 4 3, and here we will add an happiness, but on this case we will not add happiness because 6 is equal to 6, so we will not be adding happiness here. But what if we did it like this: 6, 3, 4, 5, 6? So then we will add at all the positions. So this is the maximum element and this is the sorted array remaining. So this is the problem with reverse sorting. We can reverse sort and swap the 1 and n-1 index. What's the problem in this case? 1 and n-1. Yes, you can do that. Since n-1 will be the smallest element, that will work. That will always work. There can be multiple strategies in this problem. The main crux would be that the first element would be the maximum and then the second element would be any element that is not equal to the maximum. If you follow any strategy that implements this, then you will get the right answer. That shouldn't say wrong swap. Basically, there might be this problem. There might be this problem since n is greater than equal to 1, then there is you won't always be able to swap the first and n-1th element. Basically the length can be length can be equal to 1 and then you won't be able to swap. That's the problem. How to be good at ad hoc? Just keep on solving more problems and you will get better at all the topics. There isn't any specific way to get better. You will just solve more ad hoc problems and you will get better at ad hoc. Generally, you don't need to specifically practice for ad hoc since that is not you'll just get better at it with other topics only. So okay, so I think let's move on to the next problem. I place the smallest element in the index 0, max at 1, rest just in ascending order. Again, this can also work since obviously what we have here is small, then max, and then the rest elements. So clearly we will add +1 here and we will add +1 here since small is also not equal to maximum. And once the maximum element comes, small plus max will be greater than all the elements here. So we will add our +1 at every other index. So you can follow multiple approaches. Bro, see my approach. We can reverse sort the distinct elements and then place all the remaining elements in any order. Yes, again you can do this also. Basically, when we reverse sort the distinct elements, you will be placing the first element as maximum and the second element as the second maximum, which is different from the maximum value, not equal to maximum value. And then you can just place the remaining elements in any order and you will get the maximum happiness score of n. So that will also work. But I did completely different thing. I took left and right and made it such that it never made double. Never made double. Yep, there can be multiple approaches. Just this is like the thing that you need to observe in this problem, and then you can just do anything. You can do anything. You just need max element before the other elements. So, yep. Okay, so I think let's move on to the next problem. So the next problem is Subarray Maximums. You are given a binary string S of length n. Your task is to find any permutation P of 1 to n that satisfies the following condition. For each index I, 1 less than equal to I and less than equal to n, if Si is equal to 1, there exists a contiguous subarray of P having length I whose maximum element is I. More formally, there must exist a pair of integers L, R such that R minus L plus 1 is equal to 1, R minus L plus 1 is equal to I, and maximum of PL till PR is I. And if Si is equal to 0, then for every contiguous subarray of P having length I, its maximum element is not I. More formally, for every pair of integers I, LR, again that R minus L plus 1 is equal to I, it must hold that maximum of PL till PR is not equal to I. If there are multiple possible permutations that satisfy the required condition, you may find any one of them. If there are no valid permutations, print the single integer -1 instead. And the permutation of 1 to n is an array of length n that contains every integer from 1 to n exactly once each. Then the constraints for this problem are again similar to the last problem. T is still 1e5 and n is still 2e5 and s is a binary string, so si belongs to 0, 1 and the sum of n over all test cases will not exceed 2e5. So again, due to this constraint, the expected solution would be of O of n or O of n log n complexity. O of n square would be too many operations. Problem 4. So basically, we need to find a permutation P such that according to the binary string, if Si is 1, then there must exist a subarray of length I with maximum element as I, and if Si is 0, there must exist a subarray of there must not exist a subarray of length I with maximum element as I. So basically, given these two conditions, we need to find a suitable permutation P, and if there is no such permutation, then the answer is -1. And permutation is nothing but, definition of permutation is arrangement of numbers from 1 to n such that each appears exactly once. So this was the problem. Let's see the test cases. The first test case is 101. 101. So basically, there must be an array of size 1 with maximum 1, an array of size, there must not be an array of size 2 with maximum 2, and there must be an array of size 3 with maximum 3. So we have to make a permutation P with the numbers 1, 2, and 3. So let's just try this order only. So now there is a subarray with of length 1 with its maximum as 1, and there is also a subarray of length 3 with its maximum as 3. So these two we are satisfying. But there is also a subarray of length 2 with its maximum as 2. So we are also satisfying, we are not satisfying this condition. So basically this permutation will be incorrect. So what we can do is we can we can exchange these two, so that 2 is now away from 1. So 1, 3, 2 will be the new permutation, and we have this, and there is no array where 2 is the maximum. No subarray of length 2 where 2 is the maximum. So this will be the answer for this test case 1, 3, 2. 2, 3, 1 will also work. So basically there can be multiple solutions. Here also these two subarrays are 1 for 1 and 3, and there is no subarray with 2 as its maximum. So again this is also a solution, and this is also a solution. So let's see the next test case 0, 1, 1. 0, 1, 1. So basically this would be a -1, because no matter how we make our permutation, it will always have 1 at some position, and the maximum of this 1 length subarray will always be 1. So basically for this we cannot find a permutation, and this is also our first observation, that if S1 is equal to 0, then the answer is -1. We also saw one more thing that similarly can be said for n also, because we can just take the whole permutation and its maximum would be n only. So that would be an n length subarray having its maximum as n. So similarly, if Sn is equal to 0, then also the answer is -1. So these two conditions, I'll just remove this. So these two conditions, these are our observations. So let's move on with the test cases. So 1, 0, 1, 1 is the next test case. 1, 0, 1, 1. So S1 and Sn are both 1. So both of our conditions are true. So there might exist an answer. So 1, 2, 3, 4. So let's just again try simply this. So we have this array for 1, we have this array for 4, and we also have this array for 3. But the problem is that we have this array for 2 as well. So this is not a possible answer. So what we need to do is, since we need to remove this subarray, right? We need to remove this kind of subarray 1 and 2. So what we can do is we can place the 3 before 2. So 1, 3, 2, 4. So now there is no subarray having 2 as its maximum, but we still have 1, 3, and 4. So this is a correct answer. And again, there can be multiple answers. 4, 1, 3, 2 also has this, and this, and there is no subarray having 2 as its maximum. So basically we notice that for 4, we had the subarray as 1, 3, 2, 4. For 3, we had the subarray as 1, 2, 3. So we missed one thing, basically, that is I length subarray having maximum as I. So this was the problem, right? This was the condition, right? So an I length subarray having maximum as I, and since all the numbers are distinct in a permutation, So this I length subarray must be nothing but a permutation of 1, 2, 3 till I. Since any other number than this inside would be greater than I. So it has to be these numbers only. So this is another observation. So let's move on to the next test case, 10101. So 10101. Then this would be, let's again try just this only, 1, 2, 3, 4, 5. Now we again have 1, but we also have 2, and we don't need 2. We don't need 2, right? So what we can do is we can place 3 before 2. 1, 3, 2, 4, 5. So that now any subarray including 2 will include 3. And the numbers in forward will always be greater than 3, right? Greater than 2. So all the numbers are greater than 2 here. So there cannot be any subarray which has maximum as 2. Then we need 3. So yes, we have 3. Yes, we have 1. Then again 4 we don't need. But currently we have that 4. So what we can do is we can put 5 before 4. 5 before 4. So now we have 1, we have 3, and we have 5. We don't have 4 and we don't have 2. So we are seeing a pattern here. Let's try to take a general test case and then try to follow that pattern. So 1, 0, 0, 0, then let's take 2, 1, then 0, 0, then 1, 1, then 0, 1. So let's take this array S. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, we just again start by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 1, yes, we do need 1, but we don't need 2. Now the thing is, we don't need 2 and we don't need 3. Let me just write these numbers here also. 7, 8, 9, 10, 11, and 12. So we don't need 2 and we don't need 3. We don't need 2 and we don't need 3. So what we can do, we need and we also don't need 4. 2, 3 and 4 we don't need, and 5 we do need. So what we can do is, we can just remove these 3 and remove 5, and we can place 5 before these 3. So what will happen? Now we don't have 4, we don't have 3, and we don't have 2 because of this 5, right? Because of this 5, these 3 numbers are, we don't have these 3, the subarrays corresponding to these 3 numbers. So, and for 5 we do have this subarray. So basically our array is all good till here. Now again 6 we do need, so let's just keep 6 here only, so that we will have this subarray. Then again similar process we can follow for 7 and 8. 7 and 8, what we can do is we can put them after 9. 9, 7 and 8. So now we don't have the array corresponding to 7. Actually this. And we also don't have the array corresponding to 8, because 9 comes now before 8 and 7. So we will not be able to make these array. So because of this, now 6 is satisfied, 7 is also satisfied, 8 is also satisfied, and we have this array corresponding to 9. So 9 is also satisfied. Now 10. So I'll just place 10 here. So 10. Then 11 we don't need and 12 we need. So we can again put 12 before 11. So 12 before 11. So using this strategy, we can generate the array. I'll just go through the strategy once more. Let's take another array. Let's take this array. So 12, 1, 2, 3, 4, sorry, 9, 12, 15, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So what we need to do is, we need to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So what we need to do is, we need to place 1, 2, 3, and then we can place this 7, and then we can place 4, 5, 6. 4, 5, 6. then normally we'll place 8 and 9, and then we can place this 13, then we can place 10, 11, 12. Then we can normally place 14, 15. So the strategy is nothing but what we are doing is simply moving this 1 here. So this 7 here. We are doing nothing but moving the 7 here, moving the 13 here, and we are all good. We can see that we have 1, we have 2, we have 3. Now we don't have 4, we don't have 5, we don't have 6. Then again 7 we do have, 8 we do have, 9 we do have. Then similarly, because 13 is now before 10, 10 we do not have, 11 we don't have, 12 we don't have, then 14 we have, 15 we have. So we can follow this strategy. Also, yep, we can follow this strategy. We just need to place this higher value before these smaller values and this value before these, so that all these subarrays we do not have, all these subarrays we do not have. So this will be an O of n algorithm. So I'll show you guys the code for that. So first of all, these two checks, if s of 0 is 1 and if s of n minus 1 is 1, basically not 1, so then the answer is minus 1 and we simply continue. Else we'll generate the answer using our process. So current is the current index and last is the last index. I'm maintaining 2 pointers. So what will happen if Si is equal to 1? So basically if Si is equal to 1, so there are two cases. Case 1 is the last element was also a 1 or the last element was a 0. So if the last element was also a 1, we can just normally put answer of cur as this number and we can increment cur. Else if the current one is this case, so basically we will be placing this back, placing this between 9 and 10. So I am using the variable last to maintain that position, and you guys will see how this last is updated. So answer of last is I plus 1. So now if s of I minus 1, if s of I minus 1 is 0, so basically this else is when s of I is 0. So now again there are two cases. If this 0, if there is a 0 before this 0 or if there is a 1 before this 0. So if there is a 0 before this 0, we can normally put answer of cur as I plus 1 and then cur plus plus. And then if there is a 1 before this 0. So basically this case, in this case, this number must come here, right? This number must come here. So what we are doing is we are maintaining last is equal to I. So this position will be last and we will increment our cur once. So our cur will come here. Cur will skip this position and then on the next position we will put the current number and move on to the next position. So I think this might be a little complicated for some of you. You guys can go through the code by line and try to dry run it. I'll just do dry run once. That will make it more clear. So let's just take this case only 111 0 0 0 111 0 0 0 111. So initially my cur is also 0, my last is also 0, and I am generating this answer array. So since this 1 is 1, we will just put the 1 here and now our cur will become 1. Again there is another 1, so we'll put 2 here, cur will become 3, 2. Cur is nothing but these positions and we are placing the element at cur. So 1, 2, 3, this will become 4. So now we have a 0 which is just after this 1. So we know that this value will be coming here, right? So we will just mark this index as last and increment our cur, then place 4 here and again increment our cur. So cur is currently on the 6, 0, 1, 2, 4, 0, 1, 2, 3, 4, 5. Sorry, 0, 1, 2, actually this will be 5. This was 0, 1, 2, 3, 4. So this is 5. So cur is currently pointing on this index, and last is now 0, 1, 2, 3. So we will move on. So this 0, there is a 0 before it. So we'll just place 5 normally, 6 normally. Then we have a 1 which has 0 before it. So we will place this 1 on this last index. So we will place 7 here. Then 8 and 9 will place normally. Then again 10, we will update this last as this index and just simply place 10, 11, 12 here. Then we will get this one. So this one we will place here 13. Then we can just do 14, 15. So that's how our array is getting generated. And this was the code for it. And it is O of n. So if you guys have any doubts, you can ask. How to enable access so that others can see my submission? I think the submission can be viewed by anyone, right? I did the same in Java, got wrong answer, used string. Is it TLE? I would need to see your solution basically to say that if it was TLE or not. But just put your submission ID or put your code in the comments, and I'll see. It should be S1 equal to 0. Where actually I was in I was in 0 based indexing. Okay, so this is 1 based, right? So this just make it as 0 and s minus n minus 1. This was in 1 based. It's basically the same thing. So any advice for ICPC? There are two aspects there. One is your team coordination and second is your individual skills. So you can improve your individual skills and also give more team contests and try to distribute topics so that your team coordination improves. So those are the two aspects which will help you in ICPC. Why not just split 0 and 1, then after printing any one group, just print all the remaining zeros less than current one? You can follow many different ways to implement the solution. You can follow any different approach to implement this solution. Implementation is not that important. I just did whatever come to my mind for implementation. But basically, it's pretty. There are a lot of ways to implement this. So I'll wait for a minute and then go to E. Okay, so let's move on to the next problem. So problem E, tournament rigging minimum. You are given two integers n and w. Construct an array A of length 2 to the power n plus 1 minus 1 satisfying the following properties. AI is equal to A1 is equal to W, and for each one from I is equal to 1 till 2 to the power n less than 2 to the power n, either AI is equal to max of A2i comma A2i plus 1 or AI is equal to min of A2i comma A2i plus 1. The number of indices among these for which AI is equal to maximum of A2i comma A2i plus 1 is minimized. Then the last 2 to the power n elements of A form a permutation of A1 to 1, 2, 3, 4 till 2 to the power n. Less formally, you are to set up a single elimination tournament bracket on players labeled 1, 2 till 2 to the power n, such that the eventual winner of the tournament is W and the number of upsets across the entire tournament is minimized, where an upset is defined to be a player with a target label defeating a player with a smaller label. So if there are multiple possible solutions, you may find any of them. And the output format is, and the constraints is t is less than equal to 1000, n is less than equal to 17, and w is less than equal to 2 to the power n. Sum of 2n over all test cases will not exceed 2 to the power 17. So 2 to the power 17 would be around 1e5, I think. So the expected time complexity again for this also would be O of n or O of n log n. Problem 5. Basically, in this problem, what we are doing is we are making fixtures for 2 to the power n players such that W is the winner and number of matches where a larger number player 1 is minimized. And basically, I'll explain what is this array with 2 to the power n plus 1 minus 1 elements. So let's take n is equal to 4 and let's try to understand this array. So for n is equal to 4, this would be, let's take n equal to 3. Actually, 4 is a large number. So n is equal to 3. So A has 2 to the power 3 plus 1 minus 1, which is 14 minus 1, 15 elements. 16 minus 1, 15 elements. And they are nothing but they are, and also we are given that the last 2 to the power n elements of A form a permutation of this. So basically so it will look like this: A8, A9, A10, A11, A12, A13, A14, A15. These would be the initial permutation, and then matches will happen. The first match between two, between two, between two, between two, and then their winner, their winner, their winner, their winner. Their winner will be A7. Sorry, A7 would be this, A6, A5, and A4. Then again, a match between these two, and match between these two. Their winner, A3, A2, and their winner, A1. So basically, we need to create this fixture table and then output this as A1, then A2, A3, then A4, A5, A6, A7, then A8, A9, A10, A11. Okay, so basically we need to decide this fixture and the result of each match. Since we can see AI is nothing but the maximum of A2i and A2i plus 1. So 5 is nothing but 10 and 11. So either one of these two, either the maximum or the minimum value, will proceed to the next round. So, and what we need to do is in these fixtures, minimize the number of upsets. Upsets is nothing but greater number winning. So basically, this condition AI is equal to max A2I and A2I plus 1. So AI is equal to max A2I and A2I plus 1. So we need to do this, minimize this, minimize these AIs. So, and also we need to make sure A1 is equal to W. Winner is W, we need to make sure that. Okay, so now let's see the test cases. So the first test case is 2 and 1. So since 2 and 1, so we'll need to decide the fixtures between 1, 2, 3 and 4, and the winner is 1. So we know that there will be 4 initial players, then match between these two, then match between these two and this. So this we know that it is 1, and we need to minimize the number of matches where the maximum higher number is winning. So let's just take this simple 1, 2, 3, 4, and here obviously 1 will have to win since it has to win the tournament. So 1, and here out of 3 and 4 we will let 3 win because 3 is the smaller number such that it is not an upset. And again 1 and 3, 1 will win. So clearly this arrangement has 0 upsets, and 0 is like the lowest number. So obviously this is the correct arrangement. So the answer would be nothing but 1, then 1, 3, then 1, 2, 3, 4. So 1, 1, 3, 1, 2, 3, 4. Then the next test case is same for 1, 2, 3 and 4, but now the winner is 2. So 1, 2, 3 and 4, but the winner is 2. So again we have these 4 players, match between these two, then these two, and the winner is 2. So winner is either from this half or from this half, right? Winner might be from this half or it might be from this half. So the other half is kind of like independent from the first half. So we know one thing currently. Basically, since the winner is 2, right? So someone will have to beat 1 to eliminate 1 from this competition. Someone will have to beat 1. And if someone beats 1, then that means the upsets would be at least 1. Upsets would be at least 1. Because someone must beat this one, someone must beat it. And if any number beats 1, since 1 is smaller than all the other numbers, so upset will be at least 1. So this is the first observation. If the winner is greater than equal to 2, then upset is at least 1. So let's just again take the same as last 1, 2, 3, 4. Now obviously we will let 3 win here and we will have to make 2 win here. So this is an upset. This 2 was an upset. Then again between 2 and 3, 2 will win. But which is the smaller number, so it is not an upset. So again this will be the correct answer here since upset is equal to 1. 2, 2, 3, 1, 2, 3, 4. 2, 2, 3, 1, 2, 3, 4. So let's move on to the next test case. Now we have 3 and 8. So 3 and 8, right? So we have 1, 2, 3, 4, 5, 6, 7 and 8, and the winner is 8. So again upset will be at least 1, right? So let's try to make a fixture. These two, these two, these two, and these two. Okay. So basically 8 is the highest number, right? So any match that 8 wins, that will be an upset, because the match will obviously be with a number that is lower than 8. So obviously, since everybody is playing the same number of matches, not everybody is playing the same number of matches. Basically 8 will be playing 1 and 2 and 3 matches to win. So basically number of upsets will be equal to 3, and we can just write any formation. We can just do simple this 1 2 3 4 5 6 7 and 8. Here we can just make 1 win, 3 win, 5 win. Here 8 will have to win, which is an upset. Again 1 will win, 8 will win, which is an upset. Again 8 will win, which is an upset. So upsets is equal to 3, and that is like the minimum number of upsets. So if here again we have another observation. If winner is 2 to the power n, then we will have n upsets. Because obviously every match that 8 plays, 8 will win, and that will be an upset, and rest all we can just let the smaller number win. So that is the answer for this test case. So 8 1 8 1 3 5 8 1 2 3 till 8. So I think there is some other formation given, but again that will also have a number of upsets equal to 8. I can show you that, I think. Yes, let's just make this formation and see number of upsets. So 2 3 8 1 6 7 4 5, 2 3 8 1 6 7 4 5. Then the next is 2 8 6 4. So 2 8 6 and 4, and then 8 4 and 8. So 8 4 and 8. So again this is an upset, this is an upset, this is an upset, and rest all the shorter number is winning. Smaller number is winning. So again the upsets is equal to 3. So this was the answer for this test case. Let's move on to the next test case, which is 411. So now this is a very big test case. Let's do it. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So these two, 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 and these two. So the fixtures will look like this, right? So 11, let's try to do this smartly now, since this has become a very big test case. So, okay, winner here. So, okay. So let's divide this in two parts, right? So these two parts, let's divide it in two parts. And since these two are symmetrical, these two are very symmetrical to each other. So we can just put 11 in any of the parts. So let's just put 11 in this part. Now again, in this part, every position is identical, right? Symmetrically, we can say that every position is identical. This, all the positions are identical. So it doesn't really matter that where do we put 11, because if there exists some arrangement, then no matter where we place the 11, we will have an arrangement. And if there is no arrangement possible for that number of upsets, there will be no arrangement possible. So let's just put 11 here and see what happens. Basically, I am saying that no matter where we put the 11, we can always find an arrangement that gives the minimum number of upsets, since every position is identical, right? So 2 to the power n by 2 numbers will be inside this half, right? Half of the numbers will be here, and the rest half numbers will be here. So obviously we will always let the smaller number win if we can make the smaller number win. Basically, the only constraint we have that is the 11 must always win. 11 must always win. and we will let all the other matches, we will let the smaller number win. So basically the winner of this half will be the smallest number out of all these. So smallest number out of all these will be the winner of this half. So smallest number of whatever these. Okay. And the winner of this half will be 11 only, right? Okay. So now if there is basically we kind of see a sub problem here now. We see this sub problem. We again have a very similar arrangement like this. And here we have 11. Sorry. Here we have 11. So this is this sub problem. This sub problem we are looking at. Here was 11, here also 11, 1, here also 11, 1. So basically, again we have this problem, and we can say that the smaller number out of these four will come here. Smallest number out of these four will be coming here, right? And then we have another sub problem. Similarly, if we go one step back, then we have another sub problem. So where this number would be the smaller out of these two. So this number will be the smaller out of these two. And if we go one more back, then this number is the smaller out of these two. This number is actually just this. So basically, the four matches where upsets could happen: this match, then this match, then this match, and this match. So if this number is greater than 11, then this upset will not happen. If these two numbers are greater than 11, then obviously no matter which will win, this upset will not happen. Not this. This upset will not happen. This. And if these four are also greater than 11, then this upset will not happen. This upset will not happen. And if these 8 are also greater than 11, then this upset will not happen. So basically I think I'll make the diagram again and explain, and you guys will understand. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So these two, 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 these two. So here we have 11. So if this number is greater than 11, then this upset will not happen, right? This match upset will not happen. And if these two numbers are also greater than 11, then this match upset will also not happen, because if these two numbers are, let's say 13, 14, then this will be 13, right? And 11 and 13 match again will not be an upset. Then the next upset we can avoid is by having these four numbers also greater than 11. So if these four numbers are greater than 11, then this will be greater than 11. So this upset will not happen. And if these 8 are also greater than 11, then this upset will also not happen. And that would be the case where 0 upsets happen, where the W is 1. So basically, in order to minimize the number of upsets, we need to avoid as many upsets as we can. So what we can do is, we can place 12, 13, 14 and 15 here after 11, so that as many groups as we possibly can will have numbers greater than 11. So this group will now has number greater than 11, so we avoid one upset, we avoid another upset, but this upset we won't be able to avoid, and this upset also we won't be able to avoid, because again we will have to battle their smallest and we will have to battle their smallest. So their smallest will be less than 11, their smallest will be less than 11. So now again there can be one argument. What if we not place this 14 here and actually place this 14 here and somehow make this 14 come to this point and then have the match between 11 and 14? But obviously if 14 is not the smallest element in this group, then there will be at least one upset happening, so that 14 is the winner of this group. and if there is one upset happening, so there will be greater than equal to one upset happening. So basically this is the best case scenario only. So if upset is happening because of this group, there will be equal to one upset only, this battle. So this is the type of, I'm sorry, actually there is a lot of noise in my hostel right now. So basically we can follow this type of strategy so that as many groups as we can, starting from the smaller groups. Basically this group only requires one element, then this group requires two, then this group requires four, and then this group requires eight. So we'll just place the elements like this: 11, 12, 13, 14, 15, so that as many groups as we can will have elements greater than 11, so that upsets won't happen. So in this case we can avoid two upsets, and then we will have this and we will have this upset, so that our total number of upsets will be two, this and this upset. So two upsets, and the answer will look like this: 11, 12, 13, 14, and then we can just place the number likewise: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 16 also we have. 16 also we have. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, placing 16 also does not change the number of upsets, because we need all four of these greater than 11 for decreasing the number of upsets. So, yep. So here 11 will win, here 13 will win, here 15, here 1, here 3, 5, 7 and 9. Here 3 will win, here 7 will win, here 3 will win. So 0 upsets here. Here also 1 will win, here 11 will win, here also 11 will win, here also 11 will win. So basically this was an upset and this was an upset, so two upsets. So that will be the answer for this test case. And I think you guys understood how we can generate the numbers. We can basically put these, all the numbers greater than W here, and then all the numbers remaining, and just do the fixture. If the match has W in it, then W wins, otherwise the smaller number wins, and this will be the lowest amount of upsets. So to implement this, we can basically first make this array, and then using this array we can make this array, and so on. We can just make the arrays and concatenate them. I'll show you guys the implementation. So vector of vector answer, basically this will contain this array, then this array, then this array, then this array, basically in levels. This array, by this array I mean 11, 13, 15, 1, 3, 7, 9, 5, 7, 9. So this array, so basically I'm storing the values in the levels. So initially in the first level, I'll just create this vector temp, where from W till 2 to the power n I will have all the elements. Then after that from 1 till W minus 1. And then I'll push back that in the answer vector. So now using this array, I'll create the next level. Using this level, I can create the next level. So I'll run a while loop, and this while loop will be basically if the last level pushed back in the answer vector, if is not of size 1, then we will just continue the while loop. And if it is of size 1, then we will break. Basically size 1 means we have reached this level. So how we will go from this level to this level? We will create the vector for next level, and we will run the iteration over the last level, and we will do I plus equal to 2, and then we can just push back minimum of answer I, minimum of index I and I plus 1. So basically minimum of these two, minimum of these two, minimum of these two, minimum of these two. And if any one of those two elements I and I plus 1 is equal to W, then simply the winner of that match is W, and we can continue. No need to push back the min. So for first level we will do these matches, then for second level we will do these matches and get these numbers, and in the end we can just push back this level inside answer, and then we can just see out all the levels starting from the last level. So that was the code, and the overall time complexity would be O of 2 to the power n only. So I think if you guys have any doubts, you can ask. I'm sorry for that scream, guys. I think someone's birthday is going on in my hostel. I'm sorry for that. Somebody just screamed outside my room. So, did you guys understand the solution? Stuck at 1600 on CF. Any suggestions how to improve? Just keep giving contests and solve problems around your rating. So that way you will improve. There is no secret. That's just how you do it. Can you explain the code, please? Okay, I'll go through it once again. So basically, what I'm doing is I'm inserting the levels, individual levels inside this vector of vector answer. So basically, in this case, the first level will look like 11, 12 till 16, then 1, 2 till 10. Then the next level will look like 11, 13, 15, 1, 3, 5, 9. And then the next level 11, 1, 3, 7. And then the next level 11 and 3. Then the next level 11. So these levels I am storing in the answer of this vector of vector answer. Now how I am computing these levels? So the first level can be simply computed. I'll just create a temp vector and push back elements from 1 till 2 to the from w till 2 to the power n, and then push back the elements from 1 till w minus 1. So creating this level. Then for the next level, what I'll do is I have this while loop. Inside this while loop, I'll compute the next level, and the next level will be computed from the last level. From this level, I will compute this level, and what I will do is I run a for loop I is equal to 0 till the size of the last level and increment I by 2. And in the next level, I will just push back the minimum of these two, ith and ith plus I plus 1th element. So 11 and 12, basically we can see 13, 14, I push back 13, 15, 16, I push back 15, 1, 2, I push back 1, 3, 4, 3, 5, 6, 5, 7, 8, 7, 9, 10, 9. And for the case where any one of the team is 11, for the case if any one of the team is equal to W, I simply push back W and continue, because W has to win all its matches. So from this array, I'll create this array, and then from this array, I'll create this array. So 11 and 13, 11 wins, 15 and 1, 1 wins, 3 and 5, 3 wins, 7 and 9, 7 wins. Then from this 11 and 1, 11 wins, 3 and 7, 3 wins. Then 11 and 3, 11 wins. So I will have these arrays now. First array, second array, third array, fourth array, fifth array. And then I can just see out from the last array. First I'll see out this, then I will see out this, then I will see out this. So basically I'll start from the last, go till the 0th, and just see out every element. That was the code. Earlier with 4 question in div 2 you can reach candidate master. Yep, that I also feel is true, but we cannot do anything about it. So if you guys have any more doubts, you can ask. Can we not place W on odd place only? I think there might be another solution that implements this idea, but the main idea I explained to you guys. Can we not place, basically you could have placed W anywhere, it doesn't really matter, it is symmetrical. You could have placed 15, 16 here and 11, 12 here. So again, the problem would be still very symmetrical. To get the same optimal answer, you will have to move this group here and this group here. But that solution just doesn't look nice. It is not the way we think. How we think is like this. Okay, so I think you guys don't have further doubts, so I can end the session. Thank you.